In this video, we will be taking a look at the problem telecommunication. So in this problem, we're basically given a graph and we are asked to find the minimum amount of nodes that we need to remove so then C1 and C2 become disconnected. So here we can think of this as a minimum cut problem. And with a normal minimum cut problem, you will be asked to remove the edges and see what is the minimum amount of edges that you need to remove. Here, this is basically the same thing, but instead of removing edges, we're removing nodes. So every time we remove one node, we will disconnect all of the edges we will disconnect all of the edges that are connected to this node. So basically, we'll remove all of the edges that are around this node. And to do that, we can basically create an edge from this node to this node as itself. But think of it as linking one node to its, so we can think of this as one node with the in degrees and the other node will have the out degrees. So if we disconnect these two nodes, which are basically the same node, if we disconnect the edge between those two similar nodes, then we will not be able to connect the node in degree node to the out degree node. This means that we wouldn't be able to pass on the network using this node. So to do that, we can multiply everything by 2, so then we will have an in-between node for each of these. And so we will have the out degree node will be this current node multiplied by 2, and the in degree node will be this node multiplied by 2 minus 1. So basically this will represent the node that is receiving this network, and this will represent the node that is sending out the network. Although this can be basically considered as one node, but we're thinking of removing this node itself, which is basically the same thing as cutting off the in degree node and the out degree node. So first here, when we're reading the input, we will connect every out degree node to the in degree node on the other node. So for the first in degree node, we will connect it to this V, but here we'll have to minus by 1 because this is basically the in degree node. This is the node that is receiving in all of the network. And then we will use V multiplied by 2 and connect it to U multiplied by 2 minus 1 because here U can send signals to V and V can also send signals to U. So this edge should be bidirectional. So here, this V multiplied by 2 will represent the out degree node for V. So this node will be sending out the signals. And then U multiplied by 2 minus 1, this is basically the receiver node for U. So this should be receiving it. So we'll set those to 1, meaning that there's an edge between those. And also there should be an edge for every one of the nodes. So basically this is the node that is connected to itself. So this way we can get whatever info is from the receiver node and send it out using the sender node. So these all should be set to 1 as well, but here loops through all of the even numbers, so basically increase by 1 every time. And here you have to multiply n by 2 because now we have times 2 edges. So I mean times 2 nodes, still the same amount of edges, but double the amount of nodes. And then every time we reading something, we will basically clear this graph that we just used, because every time we use the maximum flow algorithm, we will modify the graph a bit. So every time we should start with the original graph and then start modifying the graph based on the original one. So every time I'll use this function to reset the graph and then get the maximum flow. So this is the current maximum flow from our starting node to the ending node. And here I also multiplied these 2 by 2 because here we are basically asked to find the maximum flow from the starting node to the ending node. So then when we use this maximum flow problem, we will always start at the start and then go to the end. So here at the start, we're still starting at, so let's say first we read in the input S. So we should multiply this by 2, meaning that we're sending out the node. We're basically sending out the signals using S. Because if we use S minus 1 or S times 2 minus 1, that will mean that we're looking at the receiver node. So we should do that for T instead. T should be the node that's receiving in the input. So we should look for t times 2 minus 1. So this is our maximum flow problem. So while there's still an edge from our starting node to the ending node, we will use BFS on that. So this is basically a normal BFS, but here we need to keep track of the parents for each of the node. So first we will push in our starting node, and we will get every node inside the queue. So if this node is equal to t minus 1, or since I already multiplied this by 2 here, this is basically the same thing as t times 2 minus 1. We do minus 1 because it means that this is the receiver node. We should be receiving the signal from whatever nodes there are. So if it's equal to this t minus 1, this will mean that there is a path from our starting node to the ending node. Then we should return true, meaning that there is a path from this. Otherwise, we'll keep on going through the graph and check if we didn't visit that yet. So if we didn't visit that, that node wouldn't have a parent yet. So we should visit that node. And also we need to make sure that there's an edge flowing from U to V. And also that edge should be greater than 0, meaning that it has a capacity of at least 1. Then we will push this V into the queue and then set the parent of V to U. So next time we won't have to visit it again. And then after we do BFS on that, we will get the minimum flow from this pass. And so then we can decrease the flow of all the edges in this pass by the minimum flow. So here we will just start with a very big number, and then look at the current node. So we can basically use a while loop to look at all the edges. Here we have to remember to start at t minus 1, not t, because if we start at t, we can still reach t if we check for u is equal to t instead. But if we check that, that means it will also include that extra edge that we added from this t minus 1 to t, and that is from the receiver node to the sending node. And if we do that, then that path will also be included in this path that we recorded, because the parent of t will be equal to t minus 1, and that will not be good because we could overwrite that edge, and then next time we won't be able to reach t no matter what we do. So we should just look at the path until the receiver node and not the ending node. So we'll also get the parent of this current node that we're looking at, and the edge will be from the parent of this current node to the current node. And we will check for the minimum capacity out of all of these paths. Then we'll use this while loop again to update all of the capacities. So here we'll decrease the capacity from this parent node to the current node by our minimum flow. And then we will increase this capacity from the current node to the parent node. And this is the residual graph. So then this residual graph will keep track of whether we can undo something. So the next time we do BFS, we can go through this path and then go back somewhere. And here we would just increase our total flow that we have by this minimum flow. And then this will keep on going until we've reached one, until our path is completely filled. Then that means we wouldn't be able to reach t starting at s. So then we can return our total flow. So this will give us the maximum flow for the current graph. And then here we'll just look at each of the node and see what happens if we remove that node. So first we have to make sure that our node that we're removing is not the starting node or the ending node, because it's not allowed in this case. And then here we will see what happens if we decrease this by 1. So if we decrease this I minus 1 to I by 1, this means that it's basically set to 0, and this will mean that there's no path to reach I, because this I will always be sending out the stuff, and this I minus 1 will always be receiving in the other signals. So if they're not connected, we cannot send stuff using this node, and that means this graph will just be stuck at I minus 1. So we should try what happens if we disconnect this computer, and then also remember to set the graph reset the graph to our current original graph. So then here we'll get the maximum flow again, but this time without this current node, and see what happens. So if this current maximum flow is smaller than our so the new maximum flow that we just got is smaller than the current maximum flow, this means this node should be included in removing, because here if we remove this node we would decrease the maximum flow, and that means that this edge is important in this graph, and so if we remove this node, then the total flow will decrease, and this is what we want. We want to keep on decreasing until we reach a flow of 0. So if it's smaller than our current total flow, our current maximum flow, we should set our current maximum flow to this flow and push this I divided by 2, because here we multiply by 2 for every one of the nodes. We should divide this by 2 and push this back into the answer. So then this will mean, and also we should continue, so we won't have to add this node back into the graph again, because we've decided to remove this node. Otherwise, if this node doesn't decrease the total maximum flow, it means that this node is basically useless, and you can add this node into the graph again and see what happens if we remove other nodes. So this will keep on going, and here we will start at 2, go all the way to n, which is already multiplied by 2 here, and add 2 every time, because we are looking at one node every time. We don't want to look at the input node and then the output node, just look at the whole node. And then afterwards we would have reached maximum flow of 0. Then we can print out our answer size and then loop through all of the elements inside the answer and print them out. So this will already be in order because we're starting with the smallest node and going to the greatest node.